So one thing I have to challenge you with in this section is that to be sure that you can distinguish between electrical potential energy and electric potential, because even though the two are highly related, they're not the same, completely different things really. Electric potential energy, first and foremost, is associated with a system, right? It is the energy that is in turn associated with the interaction forces in that system, the action-reaction forces. Electric potential, on the other hand, is a property of a point in space. It is the amount of work that's required to take a unit point charge from infinity and bring it to that particular point in space. Yeah, so as you run through these problems, be sure you know which of the two that you're operating with, and be able to sort of the quote, just as I did, that difference. So here's a particular problem. It's three charges. It is, if you will, a system of charges, and we're asked to calculate the electric potential. So the electric potential, by definition, is K, Q1, no, sorry, this is the electric potential energy between two charges, Q1 and Q2. And if that reminds you of Coulomb's law, which would have that separation squared, it should, because this electric potential energy is associated with Coulomb interaction forces. Right, so I've got two nanocoulomb negative charges, one nanocoulomb positive charge at the top. They're all separated by 3 centimeters. If I want to write down this total energy, I'm going to remind you of the system, I just have to add up the individual two charge interactions. If I just kind of arbitrarily call this Q1, Q2, and Q3, I've got to add up the interactions here, here, and here. Q1 to 2, 2 to 3, 1 to 3. So let's do that. So here is Q1 to Q2. Here is Q2 to Q3. 2, 3. And here is Q, what do I have left? Q1 to Q3. I think I've got that right. Okay, so that's really all we have to do. We just have to add these numbers up now. Let me pull out some commonalities. There's a K every place. Each one of these separations is 3 centimeters, so let me just call that R. And then what's left over are just these products of the charges. And if I insert the numbers now, this is 8.99 times 10 to the 9th, and I'm going to spare you the units. This is in meters, 3 times 10 to the minus 2 meters. And then each one of these charges is a nanocoulomb, so it's got a factor of 10 to the minus 9 multiplying it. So there's a factor of 10 to the minus 9, there's a factor of 10 to the minus 9. I can pull out the common factor of 10 to the minus 18. And what's left over? 1 to 2 is minus 2 times 1. 2 to 3 is 1 times minus 2. And 1 to 3 is minus 2 times minus 2, plus 2 times 2. So you don't have to stare at this too very long to see that this is 4 minus 2 minus 2. At the end of the day, it's just 0. And don't be surprised. Potential energies can be positive, they can be negative. There's nothing really of import here that this particular system has 0 potential energy. Like gravitation, the only thing we're really going to be concerned about is the differences in potential energy. All right?